Hello. So in the last episode, we talked about horizontal asymptotes on rational functions. On this one, I'm going to show you about slant asymptotes and then holes, these strange ones that we've got. If you haven't seen the previous video, we're in the middle of doing these problems right here. And we went through and recognized which ones had horizontal asymptotes and what gave us the horizontal asymptote at that equation there for it. But we have these three right here that were a little strange, because they weren't horizontal, they weren't vertical, they were what we call a slant asymptote. And we also found out that this occurs when the degree of the numerator is larger than the degree of the denominator. So this degree is 2, this one is x to the first, and so we've got this slant going on here. Same thing over on number 14. The degree up top is larger than the degree at the bottom, 2 and 1 again, and we get a different slant over here. And then this one, same thing's going on as far as the degree of the numerators go, but we have not a slant asymptote, but we got a line with a hole in it. So what's going on with that? That's not going on with these. It's making that happen. So that's what we're going to talk about in this segment today. I'm going to take number 13, write out the function, and then I want you to first factor the top and see if something cancels out. If it doesn't, then we're also going to go through and divide it out. So let's look at that. We're going to say, okay, I've got number 13 right here. I'm going to write out that function, x squared minus x over x plus 1. I'm going to factor the top. When I factor the top, I get x times x minus 1 over x plus 1. Nothing here cancels out. So instead, what I'm going to do is take and divide this out. Now, we have talked about dividing using long division and synthetic division. If you don't remember those or are not familiar with them, go back and watch my video on that. Otherwise, I'm just going to use synthetic division here because that's my favorite way to go about it. So I'm going to take this plus 1 and make it just negative 1. And I'm going to write down the coefficients of the numerator. I get 1 and negative 1. This is synthetic division, by the way. And so from that, I'm going to drop the 1, multiply, and then add. And then remember, from that, I'm going to go 1 degree less than what I'm dividing into and write down that variable. And then you've got x to the 0 there, which just gives me 1x minus 2. Now go back and look at that slant asymptote on your graph. Look at what we've got here. Here's our y-axis, if you can't see that. Right here is the y-intercept. It's at negative 2. Notice the slope of this line is 1. This slant asymptote, as we put it, we can say SA here instead of HA because we didn't have a horizontal asymptote. Oh, I'm not writing on the right paper. SA, that is equal to what I was left over with here, 1x minus 2, or you can just say x minus 2. That's the equation of the slant asymptote. That's how we found it. We divided it out. It's what our quotient here was. All right. So let's look at the next one, see if it follows that same rule. We've got x squared minus 5x plus 5 over x minus 2. Write it out and divide it out. So we've got x squared minus 5x plus 5 over x minus 2. The first thing I'm going to do is factor that numerator. All right, if it can be factored. So let's see. 1 times 5 is 5. I want factors of 5 that add up to the middle term, negative 5. I've got 1 and 5. I'm not seeing anything here that factors out. I mean, you could use quadratic formula, but we're just wanting to know, does the top factor? And if it does, let's factor it out and see if something cancels. In this case, I'm not seeing where something is going to cancel out for us. So I've got the opposite of negative 2 is positive 2. Once again, I'm using synthetic division here. Drop the 1. 2 times 1 is 2. Add these, I get negative 3. Negative 6 goes right here. Add these, I'm going to get negative 1. And so we go 1 degree less, which is x. And so what we end up with here is we're saying x minus 2 goes into this x minus 3 times with a remainder of 1. So this is still over x minus 2 here. So this portion right here is what we care about. In this case, when you have a remainder, the last one we had a remainder of 0, went into it evenly, you throw away the remainder. I know that seems strange and there's a reason for it, but this is what we're caring about right here. This is our slant asymptote. So When we divide these out, we're throwing away that remainder, and notice it's x minus 3 here. So if you go down, let's look at this one right here. Right here is our y-axis coming through. You're going to go down 1, 2, 3, and there's the y-intercept for that slant asymptote. We don't have a horizontal asymptote. We have a slant one, and it's at y equals x minus 3. Okay? So that's the general gist of finding that slant asymptote. You've got a degree in the numerator is larger than the degree in the denominator, so you divide them out, and that would throw away the remainder, and that equation right there that's left over is the equation of your slant asymptote. I'll give you a hint here. It actually follows for the rest of our rules as well. I want you to think about, let me pull up one of the equations we had yesterday. This is number 12, and on number 12, we got the degree of the numerator equals the degree of the denominator, and so we took the ratio of the coefficients there, and we got 2 over 1, which gave us 2 as the horizontal asymptote. The long way to do that is to actually divide it out and do the same thing we do with slant asymptotes, where we have x squared plus 4. We say, how many times does that go into 2x squared? Well, x squared goes into 2x squared 2 times, and then when we multiply it out, we get 2x squared and an 8 here. And then we subtract these out, we get negative 8 as our remainder, and that's still being divided by x squared plus 4. But just like with the slant asymptotes, we say, get rid of that remainder. We don't care about it for right now. This is the equation of our asymptote, y equals 2, after you throw away that remainder. So the same thing works when the degrees are the same. It's just much easier to recognize, hey, the degrees are the same. I'm just going to take the ratio of the coefficients. Same thing over here. If I were to divide out number 11 and say, how many times does x squared plus 1 go into x squared? Okay. Notice the degrees were the same, so we took the ratio of the coefficients, but look what's going on here. X squared goes into x squared. Whoops, I just lost my light. It's like the room went dark. Hold on. There we go. All better. So x squared goes into x squared 1 time. 1 times x squared is x squared. 1 times 1 is 1. I subtract these. Those cancel out. I get negative 1 as my remainder. I don't care about the remainder in this case. I'm throwing it away. All I'm searching for are where's the asymptotes. So this is the equation of my asymptotes, y equals 1. But once again, it's much easier for me to just tell you, if the degrees are the same, take the ratios of the coefficients. And that's a lot easier than doing the division problem. Look at one where the horizontal asymptote was 0, like number 9 up here. If I were to look at this and say, okay, how many times does x squared plus 1 go into x? X squared goes into x 0 times. It goes in 0 times, and this is my remainder, the x. So the equation is y equals 0. All right, we're doing that on those rules we learned in the last episode. Just the last episode made it a lot easier because you could say, hey, if the degree is less than the denominator, degree of the numerator, then you can just say y equals 0 is your horizontal asymptote. If the degree up top is the same as the denominator, you take the ratio of the coefficients. Those were all covered in the last video, but in this one we actually see that this rule for slant asymptotes works for them. It's just a longer route to get there. Now with slant asymptotes, we don't have a nice easy rule that we can follow to come up with the equation of that slant asymptote. We actually have to do the division part, throw away the remainder, and what's left over is that slant asymptote. Now, I want to caution you on something here. Sometimes we don't get a slant asymptote. Look at this one right here, number 15. Number 15, let's write that equation out. It says x squared plus 2x minus 3 over x minus 1. Don't immediately say, hey, the numerator's degree is greater than the denominator's degree. Let's just divide the thing out. Do what I said a second ago and factor out that numerator. So if I do that, I get factors of negative 3 that add up to 2. Well, I'm going to say 3 and 1 with the 1 being negative. And so the numerator factors to x plus 3 times x minus 1. And so this is what it looks like. Now, does something cancel? You bet it does. We got x minus 1 and x minus 1 canceling here. And it leaves me with x plus 3. This is what this rational function simplifies to. It simplifies to something that's linear. And if you look at it, that's the equation of this line right here. It's x plus 3. But it has this right here going on. There's a hole there. Why is there a hole there? Because the original function's domain had an error where? At x equals 1. So when I'm asking you, go back to when I said find the domain of functions, this is saying x can't be 1 because that means we're dividing by 0. But students say, but didn't it simplify to something where x could be 1? Yes, if the original problem was y equals x plus 3, you're okay with that. But that's not the original function. The function itself is a fraction. And fractions can't have zeros in the denominator. So even though this simplifies to this, it still has a history. It's got a past, right? And its past said x can't be 1. So we still have to throw 1 out of the graph. And so we put a hole here. Now, this means that all these values are good. There's a hole right here when x's value is 1, and then you go on. But you need to be able to tell me exactly where that point is on the graph. So just tell me x equals 1, there's a hole there, isn't enough. I need to know the y value. So to find the y value, this is what you do. Now that you say, okay, there's a domain error here at 1, we're going to take this and put it into this simplified version. If you put it into the original version, you're going to get something over 0, and you can't divide by 0. So this is the line we actually graph. Find out where the y value is on that line. Put 1 back in, and you get y's value is 4 when x equals 1. So our hole is at 1, 4. That's where the hole is. And notice that's where they've got it right there at 1, 4. Now, if we look on Desmos at this, let's switch over to Desmos. And let's see what we got going on here. Where is that equation? We want x squared plus 2x minus 3. It's right here. So I'm going to turn that one on, and this is from the last video. Let's turn those off. This is the line we got going on right here. Notice you don't see the hole on this graph. And so you got to be careful when you're looking at Desmos, because you're not going to be able to just go there and say, oh, it's graphed out already for me. But we know it's at 1, 4. The thing is, think about how big a point is. If you go back to geometry, we talked in geometry about a point has no width, no depth, no thickness there. So it's very, very, very small. And Desmos is graphing even those smaller points in there. And so there's so many points around the point 1, 4 that you don't see the hole there. So notice if I drag to right there, I've got 0.99, 3.99. The function is defined there at 0.99. It's at 1 that we have an issue. So I'm just going to drag along that, and notice right there when it equals 1, that's when the hole shows up. And it says 1, undefined, or it doesn't even say comma, it just says at 1 it's undefined. So there you can see, you can verify if you're graphing these and say, I got a hole here, is that correct? And you're wanting to find out, you could drag it along there. Or since I named this P of X, I could type in what is the graph P of 1. Let's see if that graphs it or not. It may or may not. P of 1, it probably just says undefined. So it's not going to graph that. We could graph the point 1, 4 if you're wanting to just kind of show this for some reason. And you could switch this if you hold down on it, you click it so it shows up as a hole. That's how when I copy and paste these into a test or quiz, that's how I make them. So if you want to represent that to someone, you could do that in Desmos to show, hey, there's a hole there at 1, 4. But Desmos itself will not put it in there for you, at least not yet. They may in the future, maybe when you're watching this, they are. All right, so that covers where we find the hole. It's when something cancels, okay? So factor out that numerator, and if something cancels, there's probably going to be a hole at that point. We got to go investigate, put that in, and find it out. Now let's look at number 16 here. So number 16 also has a hole, but it has a horizontal asymptote as well. Let's see what's going on with that one. So I'm going to say, okay, I've got x squared minus 9 in the top. I know that that will factor, right? That numerator right here factors because it's a difference of squares to x minus 3 times x plus 3. Now I want to see if something cancels here before I go dividing things out. So the denominator is x squared plus 5x plus 6. I'm going to see if I can factor that out. So I want factors of 6 that add up to the middle term 5. It's going to be 6 and 1. And taking the shortcut, I get x plus 6 times x plus 1. Wait, let's see here. Factors of 6 that add up to 5. No, that's not going to work. They don't add to 5, do they? Whoops. Sometimes I make mistakes. Start rolling through this too quickly. I got 2 and 3, right? So 2 and 3, this factors to x plus 2 times x plus 3. Now I'm going to have something right here that will cancel out. So where does it cancel out when x equals negative 3? Notice right here, I know a few things about my domain. X cannot equal negative 2, and x cannot equal negative 3. That makes the denominator equal to 0. So that tells me that there's going to be a hole at x equals negative 3. And if you haven't watched the video already on vertical asymptotes, it tells me that there's going to be a vertical asymptote at x equals negative 2. So if you look over here, negative 2, there's my vertical asymptote coming through. The hole is at negative 3, but where exactly? Remember, we're going to put it into our simplified version. These two cancel, and it leaves me with x minus 3 over x plus 2. I want to know what is my y value when x equals negative 3 so I can know exactly where that hole is in the graph. So when I put in negative 3, I get negative 6 over negative 1. Because negative 3 minus 3 is negative 6. Negative 3 plus 2 is negative 1. That simplifies to positive 6. So when x equals negative 3, y equals positive 6. So right here is negative 3, and right there is positive 6. That's how we found out where that is in the graph. Make sure when you're graphing these that you graph that particular point, that hole right there. Make sure you're graphing all the asymptotes, and we'll talk about graphing later, but those are solid points to bring up here. All right, there was no slant asymptote here because notice the degrees here are now the same. Okay, the degree of the numerator is the same as the degree of the denominator in our canceled out version, which means we're going to take the ratio of the coefficients here. What is the ratio of the coefficients? It's going to be 1 over 1, which is 1, which goes like this. Once again, if you accidentally messed this up and said, I'm going to divide this out now and see where my slant asymptote is. If you tried that, you would get x plus 2 going into x minus 3. This goes in one time, 1 times x, 1 times 2, subtract, and we get negative 5 as our remainder. We throw that away, and the equation of our asymptote is y equals 1, which isn't a slant. It's a horizontal line here, isn't it? And so that is our horizontal asymptote there. So that's how that one works out. I'll probably give you a whole lot more examples on these so we can test them out and actually start testing graphing in them. But right now, what you should know is you should know how to find the horizontal asymptote if the degrees are the same. You should know how to find the horizontal asymptote if the degree in the numerator is less than the denominator. It's hard to say there. That's just y equals 0, right? If it's up top, if it's less than the bottom, the degrees, you know it's y equals 0. And then if the degree up top is larger than the bottom, make sure there are no holes, factor and see if anything cancels, and then divide it out and find out the slant asymptote there. Okay? Let me know if you have any questions. Make sure you watch all 3 videos to know how to find out all these asymptotes and where the holes are in the graphs. And thank you for watching.